I'm Sebastian Semper, my professor is Thomas Hotz, and we are working very closely with engineers who are concerned with compressive sensing. And in that context, they proposed a problem to us and we tried to solve it. It has to do with compressive sensing, so I'll start with that. In compressive sensing, you deal with signals, which are modeled as discrete vectors in the simplest case. And we know from practice that certain types of signals can be represented very efficiently given a suitable basis. So for example, audio and images are, let's say, it's a very vague term, but let's say we're concerned with audio. That's some type of signal, and images. So for each type there exists a basis, let's call it B, such that every audio signal we would like to represent, we can do that with a sparse vector. So we only need a few basis elements to represent that signal we are dealing with. So what we say is that X is sparse, and we call it sparse if this quantity here, just counting the non-zero entries, is way smaller than n, the dimension of the signal. Yeah? And we also call Y sparse in B. And we say X is S sparse if this L0 norm, which is not exactly a norm, obviously, is equal to S. We assume that the basis is known, and here are some examples. You know, of course, most of them. And also the application and the basis that is used. So again, we have this very easy linear model. The problem now is, in practice, you normally cannot observe the signal directly. You only have evaluations of certain functionals from that signal. So we have linear measurements, and these generate numbers, in that case, real numbers, from our signal. We can design these phi's freely, yeah? And that's the sensing part. So we are sensing the signal with linear functionals, yeah? And the compression starts because the number of measurements, so m here, is way smaller than n. We hope we can do that since we know we have a sparse representation of our signal, so these two things go hand in hand together. Just for terminology, Z is called the measurement, phi is called the measurement matrix or compression matrix, and so we have a model for Z which is phi times B times X. Yeah? And yeah, the problem now is that the kernel of this product of these two matrices is non-trivial because phi has less rows than columns. So if we just want to invert this system, that's not possible. Uniquely, we have infinitely many solutions. But obviously, we have just one signal which gave us these measurements. So what we want to do is we want to get back that signal from the measurements, the right one. Yeah? And now, how can we reconstruct X or Y from this observation set? And sparsity is here to save us. So first we assume that B is the identity. I mean, that's not really loss of generality. We can just put B in phi and be done with it. And one naive approach, or one of the first approach you could have, is that you're just searching for the X, which minimizes this S0 norm. So we're searching for the X which has the fewest non-zero entries, given that it generates the measurement we observed. Yeah? It's pretty, yeah? Cool. The problem is that's NP hard. Yeah? I mean, it's a combinatorial problem. You basically have to swipe through all the possible subsets of indices that could be non-zero, look if there's a solution. There are very many of these subsets, and so forth. So the next idea you might have is, OK, let's substitute this L0 norm with a real norm, in that case, the L1 norm. Yeah, just sum of absolute values. Then this problem becomes immediately handleable. So it is equivalent to a linear program. It is convex. They are very efficient solvers to solve this type of problem. Yeah? Now the thing is, when do solutions to these problems coincide with solutions to this problem? Because that's not initially obvious when that's the case, right? Because we just swapped optimization problems. Why should that be the case? And for this, we need a notion called coherence. What we are looking at is the columns of this matrix phi. We are looking at absolute values of these inner products, and we normalize them by the norms of these columns. And we are basically looking at these two columns which maximize this quantity here. Yeah, it's very easy to calculate. Just calculate phi transpose times phi, look at the off-diagonal elements, which is the largest one in absolute value. And now this theorem says, if our phi satisfies this quantity here, and if our true x, this is the zero norm of our really underlying x, yeah, that we want to recover. If that inequality holds, then actually solving this efficiently solvable L1 minimization problem results in the same solution as if we would solve the L0 minimization problem. So for these type of systems, it's actually not NP hard. Yeah? So these are not the bad systems. And yeah, also the solution is unique, which is also nice to have. And yeah, so somehow this quantity here tells us how good a matrix is in terms of being a measurement matrix. We can choose that. Yeah, it just has the linear functions we are evaluating as rows. And yeah, since we want to do a little bit of geometry, if we look at this quantity here, it's basically yeah, if you normalize phi to the unit sphere, which is not really an issue, then the columns obviously are just points on the sphere. And this maximum is attained by those two columns where the columns themselves or their antipodals are closest to each other. Yeah? And that's also somehow intuitive, because if two columns are really, really close to each other, then it's really hard to distinguish them by a measurement. Yeah? So the closer two columns in that matrix are, the harder it gets to distinguish these two, and we don't really know which support entry of X is active or not in our signal. Yeah? So it's somehow a rough approximation for one-sparse vectors. So what we do is we consider these columns of phi to be in a projective space. In the normal way, we equip it with the geodesic distance. So it's just the angle between the columns. And now we can rephrase the coherence in terms of distance in that projective space. Yeah, very easily. This absolute value here is maximized if we minimize the cosine of the angles. Yeah? So mu, this coherence is larger than some, smaller than some mu hat if all columns have pairwise distance of at least arccos cosine of this mu hat, yeah, in the projective space. And it's smaller than mu hat as well if, now we're getting to another notion, if the columns of phi are a packing of non-overlapping balls in that projective space where the radii are exactly half of this. Yeah? So now we are rephrasing this distance problem to a packing problem. So we're trying to arrange open balls in the projective space with a certain radius such that they don't overlap. So the number of measurements we take of our signal y corresponds to this dimension of the projective space. The size of the signal is the number of balls to pack, because the columns are now the centers of these packing points. And the quality of phi is basically the radius we can achieve at or the radius we achieved when doing this packing, such that it is a packing. Yeah? So obviously we want to make this radius as large as possible, yeah, because that minimizes this. And for the conventional projective space, you can just take a result for the sphere, because on the sphere, packing problems have been an active topic of research for several decades, I think. So we have here the packing number which says we want to pack with distance at least this large in such a dimensional projective space, then the lower bound states there exists a packing such that we have at least this many elements, whereas the upper bound states that we only have at most these many points in a packing. So there is no packing which has more points than this. The lower bound is the most interesting for us. It has the correct scaling in M, what you would expect, since we are basically on this sphere, just half of it, at least in the projective space setting. So it has the correct scaling in M. That's what we expect. But the problem is it's not constructive. So we don't actually know how to place the points on the sphere. For given radii of the packing and for given dimensions, there are very regular packings, but in the general case, it's unknown. What we can do with it is we combine it with this requirement of the coherence to recover an S-sparse X. In that case, we can put these things together, and we derive a lower bound, which is very interesting for engineers, because engineers want to know how much measurement effort do I have to spend on that signal, on that type of signal, to have a decent chance of recovering it. So that lower bound on M tells us how many measurements we have to take at least in order to be able to recover the signal. And it involves the signal dimension, the sparsity, and it is basically derived from putting these things together. And what it says is, if you choose M large enough, then you can actually find a matrix such that with this compression matrix you will be able to recover your signal. And that's a deterministic performance guarantee. Deterministic here is only important because some people derive probabilistic recovery guarantees, but that's actually deterministic. And now we want to talk about outer products, because that's the last thing in the headline that's still missing. Now we change the measurement setup. So it's not anymore that we have an arbitrary matrix phi, but we have some structural constraints. That's the somehow disappointing thing. Engineers can't build whatever they want, so often they have some restrictions in what they can accomplish. So one of them is this. And still X is sparse and unknown, but we can design phi 2 and phi 1 freely. And this product here, I guess you all know it. It's the column-wise Kronecker product. So we take outer products of the columns of the first matrix and the second matrix and so forth, and we vectorize this. And outer products, because the things in the vectorizing operation are outer products. And channel sounding and sparsity order estimation, just to name some buzzwords, are the applications. And the take-home message here is we are not anymore able to design the whole compression matrix freely. We now have structural constraints. But the strategy is to proceed as before. As before means first derive packing bounds on a certain type of projective space. And then from this we can derive a requirement on how many measurements we have to take in order to recover a signal with that measurement setup. So we first define the space of all these outer products with certain dimension. And a lemma about just to relate the Frobenius norm of the resulting outer products with the Euclidean norms of their factors. And especially important is the second one. We want to go back to this projective space setting. So we first vectorize all these outer products, then we are again on a sphere. On this sphere, we use the same equivalence relation as before to define the projective space. And so we get equivalence classes on T, so some kind of antipodal things. And now the idea is to exploit this inequality here, you see the A1 and B1 are the factors of T1, and A2 and B2 are the factors of T2. And what this says is that the distance of the outer product is always larger than the largest of the distance of the factors. So our idea was, if we have two packings as we did before in the conventional projective space, and then we form pairwise combinations by forming all the possible outer products, then we always have this inequality here. Yeah? You see, it's always larger than the distance of A1 minus A2, and it's always larger the distance than by B1 minus B2. So if the points in these two packings, P1 contains the A's and P2 contains the B's, have a certain radius, then this radius directly translates to the outer products if we take all pairwise outer products from these two packings. But this packing will be much larger in size because it's just the product of the sizes of these two packings. So our packings look like this on this outer product space, and we can derive directly a lower bound on the packing number in such a space. Since we're just taking pairwise combinations, we have a lower bound on the packing number in such a space. And it's a little bit more constructive than the setting in the projective space, because now for two given packings, we know how to explicitly construct the packing in this outer product space. And it still has the correct scaling, what you would expect from this space here. That's cool. And as before, as I said, we proceed as before. We get a lower bound on the number of measurements for such a type of measurement matrix, such that, again, this efficient reconstruction method with L1 minimization actually recovers the same solution as this L0 minimization, which is way harder to do. And that's just something I want to cover very quickly, because it's very simple to do and not really part of the paper. How to actually get a decently good packing of points on a sphere, or in this case, on the projective space. I mean, what do you do if you want to have a nice packing of something? You put the things in and shake. That's a very naive approach, and that's what we did. And let the things maybe push each other away. So we define this potential, which basically does exactly this. If you have 2 points on the sphere and they're antipodals, all of them are pushing each other away. And we let this run for certain steps until convergence, whatever that means, so that we get a matrix phi, which is a decently conditioned matrix in the sense that its columns are pretty well distributed on the unit sphere, or in this case, the projective space. So just looking at some numbers when it comes to the coherence, so this number which actually determines the performance of the system. The dotted line is an upper bound for the coherence we derived from these packing numbers. The dotted line is a median over just random matrices. In these cases, we just generated identically distributed and independently distributed Gaussian random numbers for each entry, normalized the matrix, and calculated the coherence. And the drawn through line is what happens if you do this shaking and pushing away algorithm. Yeah? And in the case of this column-wise Kronecker product, so when the columns are vectorized outer products, you see that from the numbers here that, of course, these matrices can't have an as low coherence as the unstructured ones with the same dimension, because the set you're optimizing in is way smaller. Yeah, you see that directly. Again, we're pretty far away from the upper bound, which is not a statement of the quality of our algorithm. It's more a statement about the looseness of this bound. And, but we're working on that. So that's just for the raw coherence. And now when trying that out for actual reconstructions, so you see that each rectangle corresponds to a certain sparsity order of a vector x we are trying to recover. On the x-axis, we have the number of measurements we took, so the number of rows in the matrix we optimized for. And we considered 4 cases. We considered first the structure, or let's start with this. The unstructured cases, so the blue and the red line. Yeah? And in that case, again, we drew a random matrix with that Gaussian distribution, and we ran our optimization for some steps. And as well in this column-wise Kronecker thing here, we just initialized the factors randomly, left them as they were, and then from these we did our optimization, and that's the green line. As you can see, recovering less and less sparse vectors, so where the sparsity increases, or the number s increases, it gets harder, obviously, because these vectors are more complex, so the success rate of recovering these is lower. Yeah, so that's why the curves shift. You see also that the unstructured matrices are a little bit better than the structured ones, obviously, because the coherence, as you saw in these plots, is lower, so we expect better performance. We actually see that, yeah, always this gap here between these two and these two. Unfortunately, in the unstructured case, in these two cases, the optimization isn't really that helpful sometimes. We're not really sure why. Maybe we did because we did noiseless reconstruction. So in practice, of course, you have measurement noise, and we expect our optimized matrices to deal with that a lot better than the just randomly drawn matrices. But we didn't try that in these simulations. But in the column-wise Kronecker case, our matrices perform a little bit better. And that's what I wanted to tell you. Thanks for your attention. Which one do you mean? The lower, this one?
For instance, take this one.
Yeah.
In practice, for the engineers, is tied? I mean, did you?
No, it's. I mean, it depends on what you mean with tied. There are way smaller quantities for that, but often they are dealing with matrices phi, which are generated from a random distribution. So they just leave it at the random distribution, and then they use concentration of measure inequalities to say something about the coherence, for example, and then you can get way lower with this. Yeah, I mean, the engineer normally knows n squared. He has an upper bound on s. That's something which is really unclear. Yeah, but let's say we have an upper bound, then that's not really complicated, because what you do in practice is also for optimizing phi. It's not really an issue of computation time, because you deploy a system and you do all these stuff beforehand offline. Yeah, so the system normally doesn't have to decide what to do in a certain scenario. We implement it fixed, and all this stuff here is done before offline. So it's not that much of a problem.
Any other questions?
Maybe another remark, which will be more cool in the future. I mean, this coherence is basically just talking about one sparse vectors. Yeah? When can you distinguish one sparse vectors? And that leads you to the projective space. But if you're considering higher sparse vectors where S is larger than 1, then you're basically trying to distinguish between subspaces of order S, or of dimension S. So you're directly trying to optimize on the Grassmannian manifold. Yeah, so what you want to do basically when going from that further is you want to have an algorithm which optimizes not only for sparsity S equals to 1, which is the coherence, but also for larger ones, and then you would have to do some of this pushing away subspaces in the Grassmannian manifold. And that's really cool. That's something I want to do in the future. Yeah. Just as a, yeah.
So let's thank Sebastian again.
Thanks.